Hello everyone, welcome back to a new episode of All About Bridge Engineering. And having discussed with the practical applications of simply supported forms, continuous forms, and even cantilever forms in our previously other episodes, today we will focus on the practical applications of design of flanged beams in bridges around us. So flanged beams are generally introduced to us by our college teachers after singly reinforced and doubly reinforced beams, typically in second year of our engineering courses, and today our episode is entirely dependent upon the same. You will notice that 80% of superstructures around us are actually T-type beams or flanged beams, and we will very briefly begin our episode by first discussing how a flanged beam is actually different from a conventional rectangular beam. So notice through this sketch diagram that in a flanged beam the deck above is also helping in resisting compressive stresses, because some portion of the deck which is near to the web actually resists more compressive forces than the portion which is away from the web, and hence a concept of effective width is introduced in designing flanged beams, which is missing in rectangular beams. So it means a more portion of the structure is actually contributing in resisting forces, and hence utility ratio of the structure is more than a rectangular beam. Secondly, we will discuss what is the span range where flanged beams are generally preferred over solid X slabs, and why is it so. So to answer this question, it's just based on the total volume of materials involved. That is, your cost of the structure is directly dependent upon the total volume of materials involved. If you will plan a solid X slab above 10 meters of span, its depth will be around 1 meter, and for any carriageway you will notice that total volume of concrete involved in a solid deck slab will be way more than a girder plus deck slab system, and that is one reason why flanged beams are generally adopted in designing structures which span in the range of above 10 meters to 25 to 30 meters. Another thing to be noted is, with designing your superstructure with flanged beams, your total self-weight will be reduced, and once it is reduced, we know seismic forces are actually inertial forces. The effect of seismic forces depends upon the mass, so that will also be reduced. Now we will discuss what is the criteria based on which the total number of girders to be placed and the spacing between the same is decided. So first of all, the major factor is the total carriageway width that the structure is intended to support defines the total number of girders that you must keep. Also, having said this, there is an optimum spacing, that is, if you keep your girder spacing between 2.8 to 3.2, then there are high chances that you will be utilizing more sections of your entire structure, and that may result in an optimum solution. But if you will increase the number of girders, then the advantage of reduction of volume of total concrete may not be fully fulfilled, because as the number of girders are increased, you are also increasing the volume. And not only this, the number of girders also increase the number of bearings that are required over the pedestals, over the pier cap, and in such cases even the pier cap width may be increased. So there has to be a very detailed calculation about the number of girders that you are to adopt and the spacing between the same. Typically the spacing ranges between 2.8 to 3.2 meters, and 3 girder system, 4 girder system, 5 girder system are predominant in the bridge design industry based upon the total carriageway above. And also minimum 2 girders you have to provide at any structure even if the total carriageway width above is very small. So this was another component that we discussed, that what is the spacing and how the number of girders are actually decided. Now we will see what are the various types of flanged beams, that is T-beams in industry. Very from the ground, if we see that there are 2 broader categories. One is the cast-in-place beams and another is the precast beams. Cast-in-place means everything, that is the deck slab as well as the beam, will be monolithically casted over the pier caps, and all the shuttering and formwork will be arranged suitably. However, in precast beams, your girder may be casted at a casting yard on the ground, and then it is lifted through suitable capacity of cranes on the pier caps. And then in precast beams, one major difference is that To ensure composite action of the deck slab with the beam, you have to provide shear interface studs or what we call shear interface reinforcement, so that the composite action between the slab and the girders can be ensured at all times. And in that case, while designing such structures, you have to check it for shrinkage stresses as well as interface stresses. So now we will discuss the variation of cross-section of a T-beam along its length and how it is decided. So that is the reason I am standing today in front of this flyover. If you see, all the spans are simply supported. I had already shown you how we can decide a span is simply supported or not. See this pier cap, 2 bearings in the longitudinal direction are present, and on the adjoining pier cap again 2 bearings on the longitudinal direction are present. And if you see by this view, if I consider this span, 2 bearings on the pier cap in the longitudinal direction are present on each pier cap, and hence it is very much certain that this is a simply supported structure. Having discussed a simply supported structure like this, now I will show you how the cross-section of the T-beam is actually varied along its length. So just focus on this part. If you will see, this is a simply supported span, and normally all loads in the longitudinal direction are predominantly in the form of UDL. So the shear force diagram will be something like this as I am sketching it, and this actually helps in determining the various portions of a T-beam along its length. Now just focus on the middle section. This is half of the span, and the support section is the highest section, is the most heaviest section with a higher concrete volume. The support section has a thick web, and why it is done so? Because as per the shear force diagram, maximum shear is anticipated near supports for a simply supported beam. And yes, for a simply supported beam, we normally check the shear force at effective depths from the face of the support, and in going so, you see that the support section is extended at least till the effective depth of the entire structure. And after that, with a uniform slope of 1:6 in plan, as you will see in this sketch, the tapering of the web from a thicker web to a comparatively less thicker web is done, and in the midsection your cross-section is something like this, where the web is the thinnest of all the cross-sections. So to ensure gradual tapering, this zone, that is this tapered zone, with a minimum slope of 1:6 is recommended. However, the slope can extend gradually but not steeper than 1:6. So normally what we do in design is, to ease our simplicity and grillage modeling, the amount of the zone of support section is normally extended in tapered section as well, and then the mid zone comes by an equal volume of material from the left and the right side. So why it is done so, I told you, due to the shear force requirements, support sections are generally more heavier and the web is made more thick, and at the end, at the end of the tapered zone, a uniform section, that is the mid section, is generally preferred. So this is another way of optimizing your structural forms by using the concepts of analysis, by using the knowledge of analysis, where the shear force will be more, where the bending moment will be more. Please notice that bending moments will be more at the mid-range, and there the bulb, this is actually known as the bulb, and sufficient reinforcement is provided at the bulb near the mid zones, which can be curtailed as we move towards L/4, L/8, and all those things, providing sufficient development length as well. So this was a preliminary episode, or we can say a very brief descriptive episode of all about bridge engineering, where we discussed the applications of flanged beams. And now I will share with you how these are actually designed in practical bridge industry. You can design these structures simply by grillage analysis. Grillage analysis is a very well accepted tool in that you model entire superstructure, including the deck slab and the girders, based on their actual cross-sectional areas and stiffnesses in all directions, and then you apply all sorts of loadings that the structure is intended to take, and finally you analyze the same. A detailed episode on grillage analysis will definitely be shared in future. If you are interested in knowing the basics of grillage and if you want to learn the grillage, connect with me on LinkedIn or share your comments in this episode, and I will bring more such stuff related to bridge design industry and also what we study in books and how it is practically applied in reality. So I hope you got a little idea about all the structures around us, and in fact it won't be wrong to mention that all the flyovers that you will come across normally have flanged beams supporting the deck slab, and if you walk on the road and come across 10 such flyovers, you will notice that at least 8 of them will have such an arrangement. So this is another factor which defines the importance of flanged beams in bridges around us. I hope you like this episode. If you find it relatable, share it with your friends or like-minded people and help us ensure more such episodes in future will come, which will bridge the gap between books and reality and bring more clarity to our understanding of structures around us. So that is all in this episode. Thank you for watching till end, and I hope to see you again in some another episodes very soon. Take a closer look for the flanged beams that we recently discussed. You see there are 5 girders and 5 number of pedestals, 5 number of bearings are provided under each girder, and this is actually a precast RCC type structure. And how we can differentiate that whether it is precast or cast in place, because the top flange, this from this section we can very well see that it is a precast section, and the comparison between a precast T-beam and a cast in place T-beam, the cross-sectional details are shown by this sketched arrow. Just have a look at these. So you see in precast section your flange at the top is clearly visible, and in cast in place sections your flange at the top is actually merged with the deck slab. So this is another important difference, how you can figure out whether the superstructure is precast or it is cast in place.